spectroscopy per se. Here's a very nice, simple example. There are, in fact, more complex architectures. I've already alluded to those, and here are just a couple of possibilities. There really is a great number of possibilities indeed. One is a star-shaped polymer. What I've sketched is a three-arm star where we have three polymer arms. These can be of various molecular weights and compositions radiating from a central core. Another possibility is a comb polymer, where there is a main backbone with regularly spaced, regular length branches that is distinguished from a graft copolymer because of the regularity of the spacing and length. Two other very basic definitions before we go on. A thermoplastic is a polymer that can be reprocessed many, many times. It will melt and flow and can be reshaped. Polyethylene, as in the example of our gallon milk jug, is a good example. A thermoset is a polymer that cannot melt or flow due to covalent bonding between chains, and a good example of that is our rubber band. These chains have been covalently cross-linked. This is, again, one molecule. It cannot flow because in order to do that, the cross-links would have to be broken irreversibly, and there would be some degradation that would occur there. So this is an example of a thermoset. Common epoxy resins, the two-part epoxy you buy at the hardware store, where you mix a hardener and component B and component A to set up into a hard adhesive, is another example of a thermoset. As in small molecules, isomerism is important, and there are various types. Very briefly, there can be structural isomerism. In this class of polymers, generically, we see head-to-tail and head-to-head isomerism. That will depend to a great extent on the size of the R group. Steric congestion precludes a lot of head-to-head placement. More important is shown on the next slide, examples of stereoisomerism, where we have geometrical isomers, as in the case of cis-1,4 and trans-1,4 polyisoprene. These two molecules, which are of course simple isomers of each other, have rather different properties. Cis-1,4 polyisoprene is the base material typically used to make a rubber band. That would be cross-linked with sulfur. It's very, very flexible. Trans-1,4 polyisoprene is much more stiff and hard. It is partially crystalline, and it would be more likely to be used as a golf ball cover rather than in a rubber band. Other possibilities, especially for the generic class of polymers shown, where there's an R group on every other carbon. An example would be polypropylene, where R would be CH3. We have three possibilities, so-called isotactic, syndiotactic, and heterotactic. These can all be realized by way of synthesis methods, and because of the regularity of the first two and the irregularity of the last, the heterotactic structure, you might expect properties to be different, and in fact they are, and we will mention a bit about that later on. Now, molecular weight is a very, very key parameter in terms of dictating polymer properties. And there are two basic definitions of molecular weight, two types of molecular weight that are measured frequently in laboratories around the world. And I'd like to introduce you to those very, very briefly. The first is the number average molecular weight, which is defined as you see it, sum over the entire number of molecules, n number of molecules times their molecular weight divided by the total number of molecules. So techniques that measure this value, m sub m, n as it's called, typically rely on counting of molecules, osmotic pressure, techniques based on colligative properties. Most commonly, gel permeation or size exclusion chromatography is used. Another key molecular weight parameter is the weight average molecular weight, shown here. Notice the equations look similar except for an m, an additional m, in both the numerator and denominator. This biases the weight average molecular weight to the high molecular weight tail of any distribution of polymer chain lengths because of the squared term. Techniques that measure this value typically rely on the link between some measured property and the square of the molecular weight. That a classic example is light scattering. Gel permeation chromatography will also get this number. And a key result of these measurements is the ratio of MW to MN. sometimes called the polydispersity. That ratio gives an idea of the breadth of the molecular weight distribution. So a very narrow molecular weight distribution will have MW over Mn close to 1. In fact, a lot of biological polymers, polypeptides in particular, and you'll hear more about that from Professor David Terrell, but a lot of polypeptides, for example, have molecular weight distributions that approach 1.00. They're really very precisely controlled in terms of their structure. Let's now consider a short list of properties that affect small organic molecules. I would like to move in this direction for the next several minutes. As I mentioned before, I think there are tremendous lessons to be learned regarding the factors that influence properties of small organic molecules as a prelude to our discussion about polymers. This is my short list: molecular weight, molecular symmetry, the flexibility of bonds in the molecule to offer a variety of different conformations that may be adopted, and finally the strength of intermolecular forces. From basic thermodynamics, especially the second law of thermodynamics, you'll recognize delta G equals delta H minus T delta S. I would like to focus, given our limited amount of time, on the melting point as our key property that we will discuss and use as a handle to try to relate structure to properties. At the melting point, you will recall that the free energy of melting is 0. The melting point is the temperature at which solid and liquid coexist at equilibrium, and by definition at equilibrium delta G is 0. So the melting point then can be cast as a very simple ratio of the delta H of melting to the delta S of melting. The melting point and the delta H of melting can be easily gotten from calorimetry experiments, for example. The delta S of melting can be then calculated quite easily, and we will review briefly in just a few moments some data on some small molecules, but let me take you through the structures of some of these candidate molecules before getting to the thermodynamic data. The simple molecule N-pentane, I think, is very instructive for several reasons. Let's first consider what happens when pentane melts, and here's a crude picture. On the left, you see the all-trans zigzag configuration of N-pentane, the kind of conformation that it would adopt in the crystal. On the right is a snapshot of the disordered molten state. Now, when N-pentane melts, bond rotations along the backbone give rise to a variety of conformations that can be adopted. And I should point out again that this is merely a snapshot. There are many, many opportunities, many conformations that can be taken up in the molten state. If we recall the basic Boltzmann relationship, S equals K natural log omega, where omega is the number of permutations that a system can adopt, I think you'd agree, excuse me, that the melting of N-pentane is accompanied by a rather large gain in entropy, going from this ordered crystal with the all-trans conformation to the disordered melt. I'd like you to note that there are 3 isomers of pentane, and I have some data about these to share with you in just a moment. The one on the left, there's N-pentane again. On the right, 2-methylbutane, also known as isobutane, and at the bottom, 2,2-dimethylpropane or neopentane. In addition, there are 3 other molecules I'd like us to consider before looking at some data. A higher homologue of the N-pentane series, I've drawn N-octane here. Benzoic acid at the bottom left to introduce a molecule that has a polar functional group. And finally, anthracene, an example of a hydrocarbon that has a rather rigid planar structure due to its aromatic character. Let's now look at some thermodynamic data, trying to put a little story together for you. First, let's concentrate on the initial 3 entries, which is the pentane series. In organic chemistry textbooks, you frequently read that neopentane, or 2,2-dimethylpropane, has the highest melting point because of good packing in the crystal. The nice spherically symmetric neopentane molecule packs well, at least that is the argument, and therefore greater intermolecular forces need to be overcome on melting. If you notice, the delta H of melting data indicate that for neopentane, that's the smallest of the three. So that can't be the reason for the higher melting point of neopentane. And in fact, you have to go to the entropy term to understand this. Notice in comparison of the two extremes, N-pentane versus neopentane, the entropy of melting for N-pentane is rather high, greater than a factor of 4 compared with neopentane. This is because of all those conformations that can be adopted in the molten state that I tried to illustrate earlier. For neopentane, it can tumble. There's translational entropy. The methyl groups can rotate, but there is no conformational entropy like there is in N-pentane. N2-methylbutane or isobutane is somewhere in the middle. If we look at the data now for N-octane, the next highest, if we could go back to that table just very, very briefly. N-octane versus benzoic acid, something interesting to note here. Benzoic acid has a far greater melting point, and that would be usually ascribed to the fact that there's a carboxylic acid, and these intermolecular forces are far stronger than those operating between N-octane molecules. However, if you look at the data, in fact, the delta H of melting is actually smaller than N-octane. The reason for the high melting point of benzoic acid is the small entropy of melting compared to N-octane. Why is that? Well, the forces are so strong between carboxylic acid residues that dimers, in fact, persist in molten benzoic acid, severely reducing the entropy. So the point I'm trying to make here is that strong intermolecular forces can raise melting points, not necessarily by raising the delta H of melting, but by lowering the delta S of melting, by confining the number of permutations, the disorder, essentially, in the molten state. One last point about this table would be the data for anthracene. Anthracene, of course, is a planar, rigid molecule. Notice its melting point is quite high. This is, again, because of entropic effects. The delta H is not significantly greater than that of, for example, N-octane, and in fact is much less than the C25 N-alkane analog. The conformational flexibility of anthracene is virtually non-existent, and I think there's some interesting lessons here about building these kinds of structures into polymer chains. Lesson number one might be, if you want to raise the melting point of a polymer, you might elect to introduce segments within the backbone that are rather conformationally restricted. In fact, that is what we do in polymer design. As you might expect, the melting point increases with molecular size, and I've got data here for N-alkanes up through about C15. There's a zigzag tendency in this trend. We can discuss that if you wish during the Q&A, but that's typically the result as you go up the homologous series ladder, and that eventually damps out. But notice two things. One, the melting point increases predictably as the size of the molecule and its surface area increases. The van der Waals forces that are operating increase in magnitude. Second, it looks like the curve is starting to turn over, and that the increase with number of carbons further out might not be so pronounced. That's an interesting result that we'll come back to as well. Let's turn our attention to amorphous solids now.